Section 1.6, we're going to talk about solving linear inequalities. A linear inequality is something that looks like any of these. It has the symbol less than, greater than, less than or equal to, or greater than or equal to. The only difference between an inequality and an equation is an equation has an equal sign, an inequality has an inequality sign. And a solution to an inequality results in a true statement. So the solution is anything that makes your inequality true. Let's talk about graphing the solution. Let's say we already solved our inequality and our final step is to graph it. So we're going to kind of work backwards. So if our solution was x is less than 2. In inequalities you get more than one answer. With equations you'll get an answer that looks like x equals 2. That's one answer. X equals 2, that's it. Inequalities, you get more than one answer because if x can be less than 2, anything less than 2 will work. -7, 0, 1, anything that's less than 2 is a solution. So the solution, or the number that makes this true, is anything less than 2. So when we graph this, I would like you to go at least 2 numbers to the left and to the right when you graph these. We're going to have an open circle at 2 because of this less than sign. It cannot equal 2. So it has to be an open circle, and it's anything less than 2. Over here on the other side we have x is greater than -1. So we make our little number line. And this time we have a closed dot at -1 because it's greater than or equal to. One of our solutions can be -1, so we can put a dot there. And then anything greater than that. Now you can also have compound inequalities. And here we're either going to have what's called an AND statement or an OR statement. An AND statement looks like this. X is in between 2 values. And your answers are going to overlap. Here in OR statement, your answers are not going to overlap because it's one thing or the other. So here if we're graphing, x has to be in between -1 and 2. So when we go to graph this, both of these signs are just less than. They're not less than or equal to. So our circles are going to be open because it cannot equal -1 or 2. And then you're going to shade in between because x is in between these two. X has to be less than 2, which we are, and greater than -1, which we are. If you have a hard time reading this, you can rewrite it. If you look at them separately, x has to be less than 2. You have to read it going from right to left to read in the other direction. So you have to read this way. X is greater than -1. That's how you read these AND statements. So over here with the OR statements, those are a little bit easier, some people tend to find. So here, this is a less than or equal to, so at -2 we're going to have a closed dot, and at 1 we're going to have an open dot, and x has to be less than or equal to -2, so we go less than, or greater than 1. So OR statements, there's going to be a space in the middle, and your shading is going to go in opposite directions. So let's actually solve these. Let's talk about a couple properties first. Solving inequalities and equations are the same, except there's one exception. Anything you do to one side, you have to do to the other, just like in equations. But if you ever multiply or divide by a negative number, you must flip your inequality. So if you have a less than, it becomes greater than. If you have a less than or equal to, it becomes greater than or equal to. So if you ever multiply or divide either one by a negative number, you must flip your sign. So let's actually solve some. Let's start with this example. It's exactly like an equation, just treat this as an equal sign, except if you would multiply or divide by a negative, you have to flip your sign. So our goal is the same. We want to get our x's to one side and our constants to another. So then we subtract our 2 to the other side. And we just subtracted 2. We didn't multiply or divide by a negative, so we're okay. But now my final step, I'm going to divide by -2. So I need to flip my sign. So my final answer is going to be x is less than or equal to +3. Now to graph that, I didn't leave a lot of room to graph that, so I'll go up here, I guess. I'm going to have a closed dot because it's less than or equal to at 3. And it's less than, so I'm going to shade less than. So I want you to go ahead and do this one in your notes. Solve for x, find the solution, and then graph it. Let's do one and statement together. This is an and statement when there are two inequalities and your variable is in the middle. The goal is the same. You want to get x by itself. So whatever you do to one side, you have to do to all sides. So here, if I'm looking at the middle part and I want x by itself, my first step should be to add 10 to get rid of it. Not only do I add 10 here, but I add it to every single side. So I will have 6 is less than 6x, because these cancel, less than 24. My final step to get x by itself is to divide by 6, and I do that on every single side. So I have 1 is less than x is less than 4. And then I graph my solution. So here these are both open dots at 1 and 4, and x has to be less than 4, so less than would be this way, and x also has to be greater than 1, so it's going to be shaded in the middle. And statements are always shaded in the middle. They overlap. Or statements are the ones that you shade in opposite directions, and the or statements actually say or, so you should know. So on these you're going to solve each equation separately, each inequality, not equation. So you're going to solve these separately. I'm going to start on the left side. So to solve for this inequality, I'm going to subtract 5 first, and then divide by 3. So I get x is less than 2, or over here I add 7, and then divide by 5, and x is greater than 6. So now to graph this, you make your number line. And I'm going to have, again, both open dots because it's no or equal to at 2 and 6. And x is less than 2, so I go less than, or greater than 6. So I shade greater than 6. And again, or statements shade in opposite directions, so that is correct. Last thing I want to do is go through a short story problem. So in these, you're going to have to set up an inequality, and that's the hardest part. So in this problem, you have $50 to spend at a county fair. You spend $20 for admission. You want to play a game that costs $1.50. Describe the possible number of times that you can play the game. So at the fair, you have $50 to spend. That means you cannot spend more than $50. But you could spend all of it, so you could spend $50. So we have to spend less than or equal to $50. We can't spend more than that because we only have 50. But already you spent $20 for admission. And now you want to play a game that every time you play it, it costs $1.50. So you spent $20 plus you're going to spend $1.50 every time you play the game. And I said your key word is anything that says every time you do something, or it's gonna cost this much per every time, that's where your variable is gonna go, because if you play it once, you'll multiply times 1. If you play it twice, you're gonna multiply times 2. If you play it 3 times, multiply times 3. So we don't know how many times we can play it, so we're gonna put our variable there, and I'm just gonna put it as t. So the question says, describe the possible number of times that you can play the game. So now all we have to do is solve for t. So I'm going to subtract 20. And then divide by 150. So t is less than or equal to 20. So you could play up to 20 times. You can play less if you like, but you can't play more than 20 times.